Okay. So thank you, Matteo, for the introduction. So indeed, FRITES, which means Framework for Information Theoretical Analysis of Electrophysiological Data and Statistics, is a Python software I started to develop last year and is hosted on Github if you want to take a look at it. So if I have to summarize what is FRITES for, I would say that first it's really made for electrophysiological data, so EEG, MEG, and intracranial data. And the main goal of FRITES is to try to extract connective networks that are modulated according to the task. And this extraction, we try to do it within the information theoretical framework. And we also have in mind the possibility to draw statistical inferences either at the subject level or at the group level. So an illustrative example, so let's say you have 3 brain areas. The first level of analysis that you can perform within FRITES is ask the question whether there is some brain areas that shows some neural activity that is modulated according to the task. So it can be, for example, condition A versus condition B, or a regression against a model or whatever. The next question you can ask is whether the connectivity between the 2 nodes is also modulated by the task. And the ultimate goal we try to achieve within FRITES is asking the question if the flow of information starting from one brain region to another is also modulated by the task. So if you summarize a little bit the method that we usually used in neuroscience, it's mainly correlation, t-test, decoding, partial correlations. And there is this really nice paper of Robin Ince, which show that most of them have an equivalent in information theory, especially using a versatile tool of the mutual information, which measures the statistical dependency between 2 variables. So this is a really nice framework because you can really work inside this framework and do all of your analysis using almost the same tool. So within FRITES, what you can do is multi-level analysis, statistical inferences. So for example, you can perform statistic at the subject level and know how many subjects have the effect. You can perform fixed effect analysis where you try to extract some typical characteristic of your population, and you can perform random effect analysis where this time you try to build a model of how your mutual information is distributed across the subject. And this can be applied either at the node level, so really on the brain areas, or on the connectivity between brain areas. So a small example, now we are trying to validate all of the method and the statistics. So it's a visual motor task, and there is the paper of Andrea Brovelli. So in this task, the subject on the screen, there is a color that is displayed, and the subject, they are learning finger association with the color. So at the beginning, they are really exploring which finger correspond to which color, and at the end, they know the association, and they really exploit this association to get the reward. So the first question you can ask is whether there is some brain areas that shows differences between the exploration and exploitation phase, and we retrieve results from the paper where there is big differences in occipital lobes. So I forgot to say, but this is computed on high gamma activity estimated on the MEG data. And another small example, but the connectivity, especially inside the occipital lobe, is also really different from the exploration versus the exploitation phase. So I guess it's almost 5 minutes. I don't really have the timer right now, but here is the link to the software if you want to give a shot, and here is the people I've been working with to develop it. So thank all of you for your attention.
Thank you, Etienne. You made perfect time by yourself. I didn't show you the cards because I didn't have the chance to show in them before, so I didn't want to confuse you, but you were in perfect timing. And
okay,
so
perfect.
we have, I guess it's a small question in the chat asking which paper made the translation from statistics to mutual information. Do you have any idea of which one would be that?
Which paper make the translation statistic to mutual information?
Yes.
I don't really understand what you mean, Jules, by the translation statistic to mutual information. Because maybe at one point I say that your mutual information is measures the ones, okay. It's the paper from Robinins 2017, and let me know, it's this one, a statistical framework for neuroimaging data. It's a really, really nice paper where he shows the equivalent between some tools and some with the mutual information. And overall, it's a really nice introduction to information theory, and yeah, really, really cool paper.
I have a question, Etienne, about mutual information. So when you work with the image alignment, that it's kind of different with working with the electrophysiological recordings. Mutual information is both a powerful tool, but also a damnation, because it makes you align images that are very different, but then you may be unlucky and the results would be a mess if the relationship is nonlinear. And since here you are basically matching group level and single subject level recordings with the mutual information, did you have any issue in which you could have some problem in matching the two? Did you have to overcome any challenge using mutual information?
Yes, so one big challenge with the mutual information, and this is a really good question, is usually it's performed with a binning. So you have to bin your data, and usually it requires a lot of data to estimate a true covariance matrix. So in the paper of Robinins, he introduced a version of the mutual information, and I think it's originate from economics, in fact, where it's using what is called the Gaussian copula mutual information, in which you don't need binning. It's a binning-free method. However, it also means that you should have a roughly monotonic relation between your two variables. So if it's roughly increasing or roughly decreasing, it's okay. But if you have, like, for example, a curve, x square relation between your two variables, in that case, it's probably not going to work. So this is one limitation, but yeah, overall, it works quite well. And I think it's a relatively okay limitation, I would say. It's a good compromise, I would say.
Okay. And to follow up, we have another question from Jules Brochard, that is, can you elaborate on the connectivity criteria FRITES offers? How do you infer a complete graph?
So inside FRITES, we have several measures of connectivity. We have non-directed connectivity, but all of them are single trial. So it's basically computing the mutual information between two time window and between two areas. And we also have covariance-based Granger causality. So in that case, it's directed connectivity. And we have a univariate version, which it's a bivariate version, sorry. So you really look at pairwise connectivity. And there is also another package which is written XFRIT, but pronounced CrossFRIT. And in that case, we are testing a multivariate covariance-based Granger causality. So yeah, currently it's in testing, but I think the results are quite promising. So Jules, if you want to discuss, we can talk about that if you want.
So to follow up the question, I don't know if Ryan first want to ask a question just because he unmuted.
Yeah, I was just going to ask, is there any
Yeah.
reason why you presented the gamma activity results here? Was that of particular interest to you, or did you look at other bands as well?
No, okay, so in the example I show you, so it was this one. It's really high gamma activity because the paper that we are trying to reproduce and validate the method is using high gamma activity. However, FRITES is also compatible with frequency temporal investigations. So you can pass full time frequency map and see if there is time frequency clusters that are different between conditions, for example.
Do you think you're potentially going after quite a hard thing to show here with the gamma band stuff?
Sorry?
I know that some researchers struggle to get reliable gamma activity results.
Okay, you mean gamma estimation with MEC data?
Yeah.
Okay, so for that, I don't know because I didn't make the gamma estimation. It was really the work of Andrea Brovelli and his paper. Okay. And now I'm more using intracranial data. I'm way more familiar with that.
Oh, right. Okay.
But I think if you really want to dig into it, there is a repo inside our project that is called, how is it called? BV2MNE. And in this one, there is a gamma estimation, but I don't know so much the details, so I don't want to say something wrong to you.
Okay, cool. Thank you.
Yeah. And if I can follow up on what you were saying on FRIT and cross-FRIT. So I imagine that then with the FRIT, you wouldn't be able to discriminate between indirect and direct functional connectivity, in the sense that if you have three areas basically, and two are connected and the third one is connected to the other two, so there is a case that you will have a functional connectivity because of an indirect connection. With cross-FRIT, you should be able to identify that difference. Should you?
Yes. Yeah, so exactly. So the problem with Granger causality is that, for example, if you have a 3 nodes and you have node 1 that is sending to node 2 and node 3, you can have a spurious connectivity from node 2 to 3.
Yeah.
So in that case, this is one limitation of the bivariate case. And in that case, you need a multivariate Granger causality. So this is what we are currently exploring inside cross-FRIT. And so, okay, cross-FRIT is in fact experimental features of FRIT that are not included for the moment inside FRIT, but it's still open, so you can take a look at it. And in that case, this version, multivariate version, should for it. And I also have to say that the covariance-based measures not only gives you if one brain areas is sending information to another, but it's also giving you the information if two brain areas have an instantaneous connectivity together that cannot be explained by the past. So it's a complex measure, but it's really interesting, I would say.
And any final comment about the pitfalls of Granger causality, in the fact that some people will argue that it's not causality per se?
Well, it's true. I mean, I think that's why usually the people say that it's causality in the sense of Granger. So I think it's a good precaution. I don't know if it's causality or if it's just delayed activity. It's hard to say, but at least it also means that you can find and estimate the delays between your brain areas and see if they are instantaneously activated or if there is a delay between them, and how is this delay propagated across your brain areas. I think it's a safer assumption to say that.
Yeah, it's a pity that we don't have Conrad Cording in this call, because we would have a fun time then. But no, thanks for the answers, and thanks for the talk. It was very interesting. And now we will move to our last speaker, Richard Lange.